Hi, so today we're going to be looking at measurements and significant figures for chemistry. We're going to cover units of measurement, including SI units, SI prefixes, which you will need to memorize. We will be looking at significant figures, how to find them, and then how to do math with them. And then you will have lots of practice through homework problems. If you need extra practice, check out your textbook. There are also YouTube videos. I'll post for you the YouTube channels that I like, and you can use those for more additional practice if needed. Let's get started with units of measurement. So we're going to be looking at units of measurement. These are the SI, the International System of Units, or the System International, for the units of different types of measurement. So for example, mass, the SI base unit is a kilogram. We will actually be using a gram as the base unit for our metric system. So metric system versus SI is a little different for base units. But the SI base units for mass are kilogram. Temperature is a unit called Kelvin. So not Fahrenheit, not Celsius. Current is an amp. Time is second. This is luminous intensity is candela. We're not going to worry about amps and candelas in this class. The amount of something is a mole, and measurement of length is a meter. And so we're going to use the metric base units here. So the SI base units are important to know, but what I want you to be familiar with is the metric base unit, which is similar to the SI, but we're going to need to know the base units to build our prefixes on top of. So for mass, the base unit is a gram. For length, the base unit is a meter. For time, the base unit is a second. And these are the abbreviations for them. And for amount, the base unit is a mole, MOL. We'll learn more about moles a little bit later, but just know that it is just a unit of measurement. Temperature units, we don't use them as bases. So typically we don't use them as bases. There are other units. There are actually lots of other units that we'll encounter in the class. Units for pressure, units for other things. We'll use multiple base units for things like density. One of the base units I'm forgetting here is volume, which is liter. And volume is just an iteration of length, but we'll be using liter as a base unit for volume. For the most part, or I guess we can say whatever your length is cubed, and we'll talk a little bit more about that in another video about conversion factors and how to deal with that. Other units to know would be some more mass units: pound, ton. And then any iteration of gram, kilogram, microgram, milligram, those are all mass units. So volume units can be any liter-based unit. Here, I'll just put some more like kilogram, milligram. These are all mass units. Liter, milliliter, ounce. Ounce can also be a mass. That's a weird English unit. Volume could be like a centimeter cubed, a meter cubed. Any cubic length is also a volume. Time, we're really only going to use seconds, and amount, we're really only going to use moles, but there are some other units. And then there's multiple units for pressure, which we'll talk about when we get into gas laws a little bit more. and then units. There are units for lots of other things, but these are the main ones that you'll need to be familiar with. So your SI prefixes, I have a table here of lots of them. You probably will only need to memorize some of these. Look for there's a memorization list for the class, and on that you'll see the prefixes that I want you to be responsible for. That doesn't mean that you won't have to memorize more in the future or be responsible for less in the future. So make sure that as you move through your chemistry career, that you also in physics, you'll probably have to memorize some of these. Make sure that you're looking at what the instructor is expecting you to have memorized versus what they will give you on exams or quizzes. But this is a list from base unit up to 18 and down to negative 18. I think that for this class, you only need to know, I say only, but it's most of the chart, from tera down to pico. Oops. That looks terrible. For this class, this specific class, tera down to pico. However, things may change after I make this lecture video, and there may be more added or removed from this. So check your memorization list. For which ones you need to know. Now, how do I want you to know these? The decimal form is okay if we're dealing with like 1,000 or 0.001. But as soon as we get up to 10 to the 6, 10 to the 9, 12, like these, you don't want to be memorizing the decimal forms of these. And I don't want to see you using these big numbers or these small numbers in your math. So I highly recommend that you just memorize the power of 10 for each of the prefixes and know their abbreviations. So for example, I would want you to know that centi means 10 to the negative 2. That's it. I would just want you to know like how to say this, like what the abbreviation means, and then what power of 10 it goes with. Some of you may have centi memorized as like 100 things. 100 centis is a thing. So you may have like 100 centis is the base. And we'll put the base here. And that's the same thing essentially. It's just that 100 is 10 to the 2. And if you change sides of an exponent around an equality, you change the sign of the exponent. So if I bring the 10 to the negative 2 over to the other side, I just make it 10 to the positive 2, which is the same as 100. So if you're like, oh, I know 100 centimeters is in a meter. That's the same as 1 centimeter is 10 to the negative 2 meters. It's the exact same statement, but it's just another way of remembering it or thinking about it. A lot of people have a hard time with these negative exponents because they're fractions, right? So 0.01. So what this is saying is, so centi is little, it's a small unit. So this is saying that there are a fraction of the base unit in 1 centi of that unit. So it's a fraction of the base. This is saying there are a lot of little centis in 1 base, which is the same thing, right? The small thing is a fraction of the big thing, or there's a lot of small things in the big thing. However you want to memorize it is fine. Some of your online homework may only recognize one way of inputting answers and information, so you should be able to flow with that way of putting that in. If you get stuck on anything, just let me know and I can help you. But what I want you to memorize is, what is the abbreviation? You need to be able to say it like out loud, like what that is, and then the standard form. I think this is the easiest way to go about memorizing them. I'm not going to require that you make conversions between two of them. We're going to go through the base unit every time. I think that is what I've seen more effective in getting you to get the correct answer. One thing I want to notice here about micro. Micro is like, it's called the symbol here is called a mu. And that's what it looks like. But you will also see this written, especially if you go into healthcare, you will see this written as MC, micro. Because if you're writing a prescription and something is for micrograms of something, this might be a little confusing. Is that just their handwriting for milli and their handwriting is strange, or is it micro? So a lot of times in healthcare, you'll see MC for micro, but when you're typing something out or writing something, typically in sciences, we will use the mu for that. It's just like an M with a tail on the front end. So that's your SI prefixes. You will have to memorize those, and then we'll use them in conversion factors, which will be a separate lecture video. Moving on to significant figures. So we're going to talk about reading an instrument. If you watch the math basics video, we went over this a little bit, but we're going to do a few more examples here. So the rule for reading an instrument is you read one place value after the marking place value. And that is true for every reading on that instrument. So if we look at this ruler here, for example, let's say I wanted to measure something like this. Pause and see if you can make a quick measurement of that. So depending on how good your eyes are, how good your ruler is, how good the markings are. Some rulers are a little older, their markings are a little off. We're going to assume that this ruler is in centimeters, because you're always going to be using the centimeter side of a ruler in chemistry class, not the inch side, depending on, for most of your labs. I'm not going to say that you'll never encounter a need to use the inches of a ruler, but you'll mostly be using centimeters for science. So let's say this is a centimeter ruler. What is the marking representing? So let's look at a different side of the ruler. And let's look at what the marking is representing here. Each time I go up a mark, what am I adding? I'm adding 0.1, right? So this is 7, this is 8, that means this is 7.5, that means this is 7.6. So if I go from 7.5 to 7.6, I added 0.1. So this is marked so this ruler is marked to the 0.1 place. What place value is the 1? It's the tenths place. So this ruler is marked to the tenths place. Just place. So think back to your place values. What place comes after the tenths place? The hundredths place. So we need to read to the 0.01 place. So every reading on this ruler has to have 2 digits after the decimal. So if we come here, we know it's in between the 3 and the 4. Maybe some people could argue that it's right on the line for the 4, which is fine. We'll have that as an available option. But if it's not, I'm not guessing, right, that it's around 4. So I can put in a number 3 here or a number 4 here pretty solidly, depending on where I think it is exactly. Like, that's not when we're guessing. We're not uncertain about that number. We're certain about that number. It's not 5, it's not 6 here in the ones place. Now, in the ones place, I'm sure of. Now, I know you're like, oh, we don't know if it's 3 or 4, but what numbers come after this is going to give me that level of uncertainty that's in between those. So we know that it's definitely in the range of 3, maybe right on 4. If we go with the in the range of 3 here, I also know that it is after 3.9. It's not after 3.8. It's after 3.9. So the 9, I also know for sure. If I think it falls right on the line for 4, then I know for sure that's a 0. So these numbers are not uncertain. They are certain depending on what way you see that it is that it's laying out. It's going to make more sense when I talk about the uncertainty in just a second. Now, the last number that we're going to write, so this is the 10th place, so that is the place of the marking, but we have to read it to the 100th place. So we need to read one more number. Now, here is where I'm uncertain. I could say 3.98. I could say 3.99. I could say 4.00 if I think it's right on the line for 4. All of these have correct significant figures. They have the correct number of digits because it's to the 100th place. And this is telling me my level of uncertainty. Right? So with this ruler, my 100th place is uncertain. So like, is this an 8? Is this a 9? Is this a 10? Kind of that's what that is, right? When we round it up. I'm kind of uncertain at that 100th place. So the last digit here is uncertain. And that is the last number that I can write down when I'm reading something from an instrument. I cannot go farther than that. I can't say 3.980 or 3.985. I cannot make up anything after my last digit of uncertainty. So the 100th place is the place of uncertainty here. And the number of significant figures for something that you're reading is the numbers that are certain and one number that is uncertain. And that's where you stop. Okay. So taking that information, we're going to read a couple other example instruments. Here is a thermometer. Pause for a second. I'll zoom in and read what you think the thermometer reading is. Okay, what place value are the markings? The markings here are every 1 degree Celsius. We know this is Celsius because you're going to read your thermometers in Celsius in chemistry, but it's labeled here. So for every marking, we're represented 1. How do we know that? Look, there's 30, there's 40. That means that's 35. 30, 31, 32, 33, 34, 35. Every time I'm going up 1. So this is marked to the ones place. So we need to read it to the tenths place because the tenths place comes after the ones place. So I need to say point what? So here, if we have 30, 31, 32, 33, 34, 35, 36, 37. So you can't just say 37. You have to say 37 point what? Degrees Celsius. So maybe you said 37.0 because you say it's right on the line. Maybe you said 37.1. Maybe you said 36.9. These are all fine. 36.9, 37.0, 37.1. Those are all fine answers for that. You and your lab partner, whoever you're working with in the lab, can argue about what that tenths place is. So the level of uncertainty here is to the tenths place. But we know the tens place and we know the ones place. We don't know what the tenths place is exactly, but we can guess. We only get to guess one number when we're doing readings. So these are the numbers that are significant here from my reading. Even if it's a 0 here, I'm telling you, I think it's right on the line. That 0 is giving me information about what I believe to be in the tenths place of that number. If it's on the line, the last number that you write is a 0. The number you guess is a 0. Even if it was on the line right here for 30, it would be 30.0. You would still have to guess to the tenths place. Okay, moving on. These are some graduated cylinders. Why don't you pause and give me some readings, and then I'll explain after that. Okay, so you may have noticed, I know it's a little hard to see here, that something happens in a graduated cylinder, and you may have seen this before in another class, but the liquid kind of does this, okay? And we call this the meniscus. It's the cohesive property of the liquid that goes up the side of the glass or the plastic. The larger the graduated cylinder, the less meniscus you see. The smaller the cylinder, the more meniscus that you see. You always read at the bottom of the meniscus. And make sure that when you're reading in the lab, that you are eye level with that meniscus. Okay, you don't want to hold it up in the air and look at it at an angle because you're going to read it wrong. You need to be eye level straight on with that meniscus. So let's look and see what you measured here when you pause. If you haven't done that yet, pause and go through and write it down to get the best out of your lecture video. Okay, here we have the bottom of our meniscus. Seems to be like it's right on this line. Now I'm marked to every ones place. 1, 21, 22, 23, 24, 25, 26, 27, 28. So I would call this like 28.0. Usually the unit is milliliters here. Usually. There may be cases when you're measuring things at, in biology, micro or smaller or larger if you're working in more of industrial, but in chemistry lab, you're going to be reading in milliliters. And maybe you thought, now make sure you're not reading at the top here. So there's a little bit of blue, like right here. Make sure you're not reading that. That's the top of the meniscus. We're reading at the bottom of the meniscus. So which is right on the line. But anywhere near there, if you said, hey, I think that's like 27.9, that's fine. That's where our uncertainty lies. So your answer is not wrong. This next one, maybe we think this one is a little under the line here, and it kind of comes up like this. So this would be 30, 40, so that's 35, 34, a little under 34, so maybe like 33.9 here. Sure, 33.8, maybe you thought it was right in the line, 34.0. That's fine. For this next one, again, it looks a little under the line. 80, 85. So maybe we would say this is 84.9. Maybe we say it's right on the line, 85.0. Again, that's fine. And for this one here, making sure we're reading in the right direction. So 30 to 40, that's 35, 36, 37, 38, 39. So 38.8, 38.9, 39.0, all are acceptable here. Okay. Once you get measuring, when you have the right number of digits and decimal places for an instrument, every reading will have the same number of decimal places. So like, even though these are some zeros on the end, you're still going to have one digit after the decimal. And the last thing I want to talk to you about within this section is a burette. A burette measures top down, so it's opposite. So look at this burette. See how it says 21 and then 22? With these, they were all 30, 40, right? So they're measuring up. They're measuring how much they contain. This is measuring how much it dispenses, how much it lets go. So we have to make sure that we're paying attention. So this is 21 and this is 22. So this is not 22 point something. This is 21 for sure, because it's in between 21 and 22. So it's between 21 and 22. So we know it's 21 something. Now, each marking, we got to think about what that represents. This is 21 and this is 22. This is 21.5. So that means it's marked 21.1, 21.2, 21.3, 21.4, 21.5 to every 0.1. So we have to read it to every 0.01. We need two numbers after the decimal here. The top here is the top of the meniscus. The bottom is the bottom of the meniscus. And that's where we want to read, is this bottom line here. I know that it's kind of hiding, but we can use our context clues to figure out what line that is. If this is 21.5, that's 21.4, and that's 21.3. So we would say 21.30 here, or we could say, you could say, 21.29, 21.31, anything within that, close to that range is fine. But if you think it's right on the line, you would say 21.0. And burettes do read in milliliters. Okay, any questions about this section? Please see me in office hours, text, email, etc. Moving on to what's going to be your favorite topic of the whole class, significant figures. There are lots of textbooks that have a billion steps for this. I'm going to try to give you as few rules as possible for number of significant figures. So when I look at a number, I give you a number, you measure a number in lab. We have to know how many numbers are actually significant, right? So I just talked about the numbers that are significant are the ones that I know for certain and the uncertain number. So this has 4 significant numbers. These readings have 3 significant numbers. These readings have 3 significant numbers. This reading has 3 significant numbers. Sometimes zeros are significant. Sometimes zeros are not significant. So we have to have a rule for how we deal with them. If we're not measuring them in lab, if I just give you a piece of paper with numbers on it, how can you tell? So any non-zero number is significant. If you're writing down a non-zero number, that means you think that's significant. That number matters. It's either certain or one of my only one uncertain numbers. A 0 sandwiched between non-zeros is significant. So any 0 in between non-zeros, that number is significant. Sandwiches are significant. And last, a 0 that is after a non-zero number and in a number with a decimal is significant. Okay, so let me give you a number with a bunch of information in it. We'll look and see what's significant and what's not. So all of these zeros are significant. This one is a sandwich. This one's also a sandwich. And these are for our rule number 3. They come after a non-zero number, and this number has a decimal. And then everything else is rule number 1, right? It's non-zero. Now let's look at some zeros that are not significant. These zeros are not significant. They are not sandwiches. They do not come after the non-zero number, even though there's a decimal here. Now, if there are zeros after, these zeros are significant because they come after the non-zero number. These zeros are placeholders. They tell me, hey, we don't have a digit in the 10th place. We don't have a digit in this place. These zeros tell me the value. These are placeholders only. This zero is a placeholder, but also a value number. It tells me, it gives me information about that place because there's more coming. Another non-significant zeros would be like these zeros. They come after a non-zero number, but there's no decimal. Now, if I want them to become significant, all I have to do is put a decimal in the number. And now they're significant. You can do that. You can put a decimal at the end of a number without anything on the other side of it. That just says, hey, the zeros in front of me are now significant. So we're going to go through some math rules for significant numbers, and then hopefully you'll get tons of practice and homework. The addition subtraction rule says the lowest place value, it's not the lowest, let's see, the least precise significant place value. It's the best way to put it in the math equals the place value in the answer that you can have. So I'll give you an example. So when I'm doing math with sig figs like this for practice, just go ahead and do the math. And let's look at the place values. The 0 is not significant. So the least precise significant place value is the tens place. This one, both are significant. So the least precise is the tenths place. So the least precise is tens. Tens is less precise than tenths. So we have to round to the tens place here. So my answer, if I round to the tens place, would be 120. So even though I try to add this 2.9, my significance is going to cut my answer to just be 120. I know that seems weird, but that's the way significance works. And that's why you want to be measuring things in lab with the most precision that you can get. More precise place value means farther to the right. So tenths place is more precise than ones place. Ones place is more precise than tens place. The best way to look at this is to line it up by decimal place. So make sure that all your decimal places are lined up. So meaning everything that's in the ones place on top of each other, everything that's in the tens place on top of each other, etc. Now do your math and make sure again everything lines up by decimal place, by place value. And then cut it off after your least precise significant place value. So this has significant figures here and here. This 3, this 0 is not significant. So we don't really know if that's a 3 or not. This could be a 1, could be a 7, could be a 9. We don't know. So I can't really report my answer to say that's a 3 because I don't really know if that's a 3. Remember, when I'm measuring stuff, the last number that I write with significance is the number I guessed at. So with this 120, we guessed on the 2. We can't guess on the 0. We guessed on the 2. So I have to cut my answer off at that 2 because everything else is beyond guessing for this number. Even though we know the 3 is there, we don't know what that is. So we can't really know what the answer is into the ones place. So we have to cut it off. So I say, draw a line like this. Everything to the left of the line is significant. Everything to the right of the line is not significant. Now, when I'm rounding this, I can't round it to 12 because 12 and 123.9 do not have the same value. When you're rounding for sig figs, you have to maintain the same value of the number. So everything has to be in the same place value. That 1 has to stay in the hundreds place. The 2 has to stay in the tens place. So we can say 120, or we can say 1.2 times 10 to the 2. If you want to put it in scientific notation, that can sometimes be helpful to figure out your sig figs because you want 2 sig figs here. Addition, subtraction gives students the most problem because it's a little bit harder to do and you have to kind of visually write it out, or you have to make notes while you have to like jot things down to get it right. Multiplication division is a little simpler. So the rule for multiplication division is the least number of sig figs in the math. And you'll see me, I'll give you comments and things. If I just say SF, that means sig figs equals number of sig figs in the answer. This is way easier, way simpler. So if we have 0.012 times 3.95, we're going to go ahead and get our answer. I don't know why I did something that's not easy to do in my head. What? There you have it. 0.474. And now we can just look at the number of sig figs. So this number has 2 sig figs because the zeros in front don't count even if there's a decimal. Here, this number has no zeros, so it's 3 sig figs. The smallest number of sig figs is 2 sig figs. So my answer has to have 2. These zeros don't count. So I have to have 2. I need to go all the way to the 7. So that's where I'll cut it off. The number that comes after the 7 is a 4, so I'll leave it alone. Remember your rounding rules. You're going to get so much practice with this. We're going to do this all semester. And then lastly, let's do a mixed math problem. So if we have to mix up our significant figure rules, we have to do order of operations, and we have to consider the sig fig rule. It's not just the last thing you do that counts for sig fig rules. You need to track it as you go. So first we're going to do the multiplication because that's the first thing we do in order of operation. So let's do that math. We need to actually do the math. I know you're like, I can put this in my calculator and it will give me an answer. I know that, but you won't be able to tell the sig figs correctly that way. So we have 6.7184 when we get that. Now, the rule for multiplication division is lowest number of sig figs. So we both have 3 sig figs here. So my answer needs to have 3 sig figs. What I like to do is underline the sig figs of my answer, but not round it yet. Do not round it yet. Some instructors may want you to round as you go. Follow that. I do not want you rounding yet. I want you to do all of your math before you round at the very, very end. So I'm going to keep the 8.4, even though I know it's not significant. But moving forward, only the 6, 7, and 1 and these place values are significant. Now, why do place value matter here? Because the next thing I'm doing is an addition. So now when I do an addition, I have to think about my place values. And that's going to determine how many sig figs I have for my final answer, right? So 2282 goes all the way to the hundredths place. 6.71 is significant. That also goes to the hundredths place. So I'm cutting it off at the hundredths place here. There's no value here that's significant, and this A and this 4 are not significant. So everything to the front of this line is now significant. So my answer has 4 significant figures. You wouldn't, most people look at this and go, oh, 4, 3, 3, answer has 3. That's not true. The answer has 4. You have to make sure that you mark it and that you do each sig fig rule separately. So my answer here, when I round, I need to round this last number up because there's an 8 on the other side. This would be my answer here. Now, I know this seems complicated, but you're going to do this so much that hopefully it becomes a little second nature to you, but practice it all the time. I know it may seem like it's causing you a lot of anxiety already to think about significant figures and all the math you need to cover in chemistry, but it is something that is important in the sciences and you will practice it a lot. So I'm also not the type of instructor to take off full credit for sig figs being incorrect. I will take off half a point here and there. Unless the question is solely about significant figures, I might take off more, but just do the best you can with them and learn from mistakes. And that will help you remember your rules. Practice makes perfect. You have to constantly be practicing this. So I appreciate your time. And if you have any questions about anything in this lecture, please let me know.